Hello, everyone. Good morning. My name is Monique. I'm going to start the session on data and information technologies advances for agricultural modeling. Let's start with the first presentation from Shenji Wang. Let's try to have 10 minutes of presentation and 2 minutes per question. I'll let you know when we're on the
Hi, everyone. I have no idea about why they distribute to this topic. Maybe I can see, because I'm not a data producer or technician advancer. But I can see something from the user side, and you can see my research as a starter for this meal. My research topic is climatic driver of crop yield variability and failure in sub-Saharan Africa. In this topic, I will walk you through the motivation of our research and how we approach it, and the main findings, and why it matters for managing climate risk. So everyone knows sub-Saharan Africa is facing a serious food security challenging, and even though the agriculture have higher potential in this region, farmers they rely on precipitation and climate smart practice are not widely used. So under this condition, extreme weather events hit farmers hard, and the discouraging investments and community poverty in this region. To change that, we should to have a better understanding of agrimeteorology hazards and which types of hazards drive crop risk in this region. But the problem is most of current research they only focus on the yield variability, and they did and the few research try to ask whether the same climate drivers can have the same explanation of the yield failure. So, and even though few research look at the whole sub-Saharan Africa region. So based on these 2 points, our research raised 2 questions. First is how yield variability and the failure respond differently to climate hazard, and what is the non-climate hazard for different maybe yield metrics. And second, it's this risk, how they shift in the future scenario. To answer these 2 questions, we establish a research framework here. Here you can see first step, we couple the historical data at both national level and graded level, and we use the climate data to extract 16 hazard indicator, and we define 2 different yield metrics, the yield variability and the crop failure. Here, crop failure is defined as 20% drop from Olympic mean. And based on this second step, we use a traditional statistical method and interpretable machine learning method to identify the key hazard based on different age zones. And under this, we do the climate projection based on the 5 GCM from CMAP6 and output from GDCMI to define the phenology, and we can evaluate the future exposure of the risk. So the first question is, what hazard affect yield variability? From the result of both national scale and the graded scale, we found the heat and the drought stand out, and among them, the web pressure deficits show the most strongest and consistent negative relation with yield variability across all 5 cereals in sub-Saharan Africa. And for the C4 crops, millet, sorghum, and maize, their sensitivity to water-related indicator, not only in the soil moisture but also the precipitation. And when we look close, zoom in the grid level, we found for maize and rice, their variability patterns differ from region to region, from grid to grid, and the most diversity region is in the arid and semi-arid region. And when we dig into what affect failure, we should define where it is failure occurs and what the frequency of this occur. We found crop failure are more frequently in low yield region, and for the maize, we found the yield and the maize yield failure risk. It's low relative in West Africa, but it's high in the South Africa and East Africa, like Mozambique. And for the rice, we found most of the crop failure occurred in the West Africa. And we found a general phenomena that when the region yield level is below 2 tons per hectare, the crop failure frequency is increased. After that, we investigate what hazard affect crop failure. We only show a general result here from this is correlationship map we found for the blue, the shadow blue represents yield variability correlation, and the dark blue represents yield failure relationship. And we found that it's easy to understand yield failure are more sensitivity to extreme hazards than general variability. And both rice and maize, we found VPD and extreme day over 35-degree days, how many days over 35 degrees show strong negative correlation with failures. And for maize, we found the drought indicator dominant risk, and for rice, the heat indicator are more necessary. So based on our evaluate, we try to project in the future how exposure will be changed in the future. We only show the result, even though we calculate the exposure change in two different scenarios, only show the high emission scenario result here. We found both maize and rice area will experience increased heat and drought in the future, in the middle future. And for the maize, we found the average, the Tmax will increase about 2 degrees in the future, and the VPD will increase 0.15 kPa in the future. And the most dangerous, most risky region for the maize is in the West Africa, like the Burkina Faso, and the Southeast Africa, like Mozambique. And for the rice, only West Africa is risky. And both of them, we found the most risky region is in the low yield region. So I want to stress 4 maybe tips for the policy and adaptation. First, we found soil moisture, it's a key buffer against the yield failure. Second, we found so it's necessary to improve maybe irrigation in the future. Second, we found the most vulnerable region in the sub-Saharan Africa, it's Sahara and the southern Africa. And third, we should think about using the VPD and the HD 35, that means 35 days, how many days in the growing season, as a good paradox to inform the early warm system. And the last point is, if we want to try to break the risk trip, we should pay more attention to the low yield region, especially in the West Africa. So I don't want to say too much about this findings and innovation here. I want to stress some key points. First, the first takeaway is we found in the sub-Saharan Africa for the maize, the drought dominant, and for the rice, the heat dominant. The second point is maybe an innovation. We found previous research point out the high night temperature will damage the rice in the Southeast Asia and East Asia. And in our research, we also observe the same phenomena that the nighttime temperature will cause yard failure in the West Africa. And the third point, maybe we want to see something connect to the topic of this session. It's we compare two different grade level yet production data. We found the agreement in the developed country, in the European Union and United States, their agreement is very high. But in the Africa, even though at national scale their data is consistent with FAO data, but special pattern and diversity is very high in the sub-Saharan Africa region. That's all. Thank you.
Thank you. Do you have questions? Any questions? The mic's coming here.
Yeah.
The mic.
Yes, so maybe to try to link this to data methods, there must be, it doesn't sound that simple to find from all of this data what exactly are the meteorological conditions and the crop conditions that lead to failure. I mean, there are tons of possible variables that are related, that are closely related to failure. And how do you, what methods do you use to try to decide which are the really driving factors of failure?
We use a machine learning method with sharp method to identify the key hazard and use it's called sharp method to explain which hazard it contribute most to the final yield failure. Yeah, it's okay.
Thank you. We have another question, and we have time.
Thank you so much. I'm Babakar Pai from the University of Senegal. And thank you also for the nice presentation. And I think you have a very good result. I was just asking myself, why is the area where you have low yield are more risky? Do you have any explanation about one?
Low yield region.
Low yield reservoir. Why is there more risky?
Change. Oh, that is a good question, because I think last year there's a paper that show the high yield country, it's easy to suffer from shock, but maybe there is a little bit different. From my thinking, I think maybe first we don't have, maybe from the data side, we said that the data is not so good maybe at that region, especially the low yield region. And second, maybe the low yield region is located at the arid and semi-arid region, and they don't have enough water, especially soil moisture is very low in that region. That may be the reason.
Thank you. Thank you everyone. Xinjing.
So hello everyone, and hello to the kids online, and so thanks Monica for organizing this session. And I'm Xinxin. So the topic of today is trying to bridge the research and models by developing a workflow to harmonize agricultural data from published. And so many of us, sorry. Okay, many of us are crop modelers. So crop model are quite useful for agriculture, but their accuracy were quite limited by the lack of excellent calibration data. So to address this issue, we want to extract the data from published literature. But the problem is how we could do this. Actually, if you want to extract data from published, you can do it manually, or there are some natural language process, or you can do it using large language model. So here we use ChatGPT API to do this. So the publication, they are normally provided as a PDF format. This format is not good for machine to recognize. So, and some publication, they might be old scanned, and the tables inside the publication should be quite complicated. And inside the publication, there are some sections which is not relevant for crop model. So that's why we want to convert it, the PDF into Markdown file and also tables and figures and process them differently. So here we use a Mark PDF package to realize this function. And because so in step 2, we try to filter the irrelevant section from the Markdown file. And so because, as I mentioned, we want to use this data set for calibrating the crop model. So we use one crop variable dictionary. So here we use the Picasa dictionary, which developed by Jeff White. But in this dictionary, each variable there can include too many information. But our large language model, they only can deal with limited tokens. So that's why we only choose 3 columns here on here. So for each variable, the variable name and also the explanation and also the unit will be chosen. And this kind of information will be provided as prompts to ChatGPT, and then we can get our structured outputs. But because for crop modelers, we want this data could be structured and could share within different communities. So maybe to see more, here I give an example. So the left part is the unstructured Markdown file, which automatically extract from the ChatGPT API. As you see some info, so here I only show 2 variables because it will be quite complicated. So like here for fertilizer dates, so they might fertilize once, but some people, they might fertilize several times. And also the material. So maybe in one stage, they only they fertilize several times, but maybe in another stage, they only once. So this means the data format could be quite complicated. So if you want to ChatGPT to directly transfer this unstructured format to structured Excel JSON file like this, it could be quite hard. So that's why we decided to fine tuning our models. And publications, we all know they don't include all necessary weather data or soil data information for running the crop model. So that's why we decided to extract some descriptive information. It might include the longitude, latitude, and also some information, because if it's a long-term estimate, maybe in the previous years they used one side and the other they changed. So this kind of information we want to also extract to better to search for the corresponding data set. And publication, they also include some parameters which they already got it after calibrating the models. We don't want to waste this information, so we also extract it. But except this, we also need to notice that some crop model with time, they have a new updated version, so this parameters might be also changed. So we also need to extract this kind of information, like the weight model in this exchange. But one big challenge in this workflow is that the large language model, they couldn't process the figures quite good. It not means they couldn't process figures, but it means if you your figures, they have quite complicated format, so the values was not so accurate. And so here is the our target so that we want to include, so like management, soil properties, and the other kinds of information. I don't spend too much time to efface this. So we already know done is that we test after discussing with our collaborators. So we test one detailed application and try to reproduce the result. So because the weather data changed a little bit, I mean, the result was not exactly the same, but they are very similar and different treatment. And because I already mentioned, this output result is not well structured like the CASA template. So we plan to final tuning our model in the future. And so we hope our data could be used for calibrating the model, but for sure there are some challenges which I need to spend several time to do it. So thank you. Thanks, Sarah.
Thank you very much. Okay. We do have questions.
Thanks for the question. So I'm wondering, like, uh, so if we plan to use this product, and what kind of like input we should give to ChatGPT? Is that like a human language? Just say like I want the historical record of the maize planting in this city or in this latitude or longitude, and then it will generate all the information to me.
Yes, but I mean, maybe I explained it wrong, but actually we deal with the publications, right? So if you have one publication, you directly transfer it to me, and I can automatically extract all the information which you can use for running the crop model.
Okay.
Yeah.
So I still need to look for the publication by
Yes.
myself.
Yeah.
And how about like for many like papers like third level guys, like they probably like they have like an external link
Yes.
of the data sets,
Yes. Sure.
and your product can directly also extract those data. Right?
No, I don't think this is my case, because in my case, they only focus on literature. And in our project, there are some colleagues who deal with the data sets. So this is another case. They also, because to keep the consistency of the data, so they will deal with the data set you mentioned, but we will integrate it into the ICASA template, which could be used for many crop models. So that's our project.
Thank you.
Many data sets are published in several papers.
Yes.
Do your framework,
Yes.
and thanks for the presentation. It was amazing.
Yeah. So actually, we already consider this because the bushland dataset, right? They have several publications to try to describe this dataset. So what we discussed is that after we extract each the dataset for each publication, but we can extract based on this descriptive information, try to integrate it the dataset from the same location. So that's what we plan to do.
And may I ask a question?
You want to follow up with this? Okay.
Yeah. Just to follow up, one more question, and then we go to Ahmed online.
What are you doing to deal with inconsistency between papers in reporting fields? I
Yes.
tell you an example. For example, very recently with Bruce Kimball and Amish Brown, we found out that the initial nitrogen for some treatments were different between 3 different papers, very different. So, and Bruce never found that out. So yeah, and I'm sure it's not a one exception.
Yes, actually, also during our process, I mean, I also find some publications the data is correct, I mean it's not correct. So that it might due to several reasons. Maybe the units they put it wrong, or some information they put wrong. So I mean, before we publish this data, and another important step is you need to do some data qualities, right? The data quality check, and also you need to check the competence. So it's not means, but I mean, if so the data quality is very depend on the publication itself. So if they have complete data set, we will use it for crop model. But even it doesn't have necessarily data, we will use it for some meta analysis. But we need we do need to do some data check. Okay.
Yes, thank you very much. Can you tell us, share some experience about how you validated the system? So is it reliable, or is it
Yes, sure.
not
This is a very important step. Okay. So first, I mentioned that after I speak, I choose one detailed publication that after discussing with collaborators. So I use this information, and I mentioned that they don't include the weather and some weather data. So I try to based on the location and to
That's okay, but the parameters you extract from the PDF, do you extract them correctly? Always?
yeah, sure. I mean, because I mentioned the PDF, they are not very nice. So that's why I use Mark PDF package. There are several tools and also a huge package to do this. So that's why I decided to use this, because after comparison, I need to find the best one. So, but I don't spend too much time. So you can search the Mark PDF. It works quite good, and they are developing this time, and they also have some specific commands for like tables. If you do it with the PDF, even this tool is good, it doesn't work well. But if you add some commands for table specific, the result is perfect. Because I also test using ChatGPT to extract tables. You could find sometimes it not. I mean, they simplify some data, but using this package, it could work. So yeah.
My question follows the lies, accuracy. Oh, sorry.
I'm sorry, we don't have time for questions right now, but thank you. Ahmed, you're the next. Are you there?
Yes, Monique.
Yes. So
Can
right. I think you were able to share your screen. We're checking this right now, and we can present here, but you can share your screen if you want.
Okay, thank you so much. Let me share my screen, please.
Okay.
Can you
Perfect.
see my screen right now?
Yes, we're seeing your screen. You are going to have 10 minutes and then 2 minutes for questions. And I'm going to let you know when 1 minute is 1 minute 20. Okay, thank you.
Okay, can you all hear me?
Yes, we can hear.
Okay, thank you. Thanks, Monique. My name is Ahmed Khair. I am working as a scientist in Julius Kohnen Institute in Germany. Today, I am willing to present the integration of a new high-safe process-based agroforestry model with machine learning for robust simulations as a decision support system for agroforestry system. I will refer to the motivation why developing a decision support system for agroforestry is important, and what is the current limitations, the why hybridization is important, then moving to some preliminary result from our approach and the next step. So agroforestry could be defined as the landscape practice where we can produce tree and crop from the same land unit to ensure some ecological, environmental, and other benefits like carbon sequestration, improving soil health and soil properties, microclimate regulations, and other economic benefits to mitigate climate change. But this is a complex system where there is a complex interaction between crop, tree, and climate, which moving us to develop a robust decision support system for robust simulation in different environments. So the motivation is the urgent need to develop decision support system in agroforestry is to simulate the complex interactions of crop and the tree growth across different seasons and environments. HiSafe is a new three-dimension process-based agroforestry system, but still has some limitations. So we are working to hybridize machine learning with HiSafe to see if we can overcome such limitations raised by HiSafe. So the challenges is the limited research data, because we need detailed data set for tree, crop, and the climate interactions, and this in different environments to use the robust and global decision support system. This complex interactions need more detailed decision support system to cover all tree, crop, and the climate interactions. And to present, there is some or little number of agroforestry models like high safe, APSIM next generation, and other models. But when reviewing the literature, we found that high safe achieved the most robust results. Also, it has some limitations. The conceptual approach to solve such limitation is to collect and manage current and historical agroforestry dataset, which is required for developing the process-based model. These dataset are used to parameterize high-safe three-dimensional model for not only simulate the agroforestry, but also to simulate the monocrop to enable us calculating the land equivalent ratio after that. Then hybridization with machine learning model to see how can we reduce the computation power and globalize our approach. So what is HiSafe and why we are using HiSafe? HiSafe is an agroforestry model, three-dimensional model developed by INRA team in France. This model enables us to reduce the landscape into a simple, replicable unit, which is in a three-dimensional spatial explicit voxel grid. So this is high specialized model, and there is a periodic boundary conditions allow us to make the scene to be repeated in all directions. So in this case, we can minimize the edge effects and the simulated stand level interactions. So if we see now, if the cell, if 1 meter in 1 meter resolution, we can see the cell could be divided in different voxels, and each voxel divided include different layers. So detailed three-dimension model, which is important in agroforestry simulations. There are many detailed data set and some complex data set required for HiSafe to be parameterized and used, like the site description, like altitude, latitude, slope, and other parameters. Soil description, and in this case, we need detailed at least 4 meter depths data set to be used for parameterization, and the tree initialization, different data set required for tree, like the cultivated alley, the orientation of planting tree, detailed data set of weather data set, and the crop management data set, and also crop rotations included in HiSafe. This detailed data set is a major driver to parameterize the model. The integration with machine learning is very important, and we are working right now to reduce the computation power and improve the robustness of simulations. So first step to build this hybrid approach is to collect agroforestry and microclimate data set, which will be managed after that, and to specify in this data set, if the data set is insufficient in simulation, we can make and desensitize detailed data set using HiSafe default values, and using mass simulation and sensitivity analysis using different environment CRs and management and scenarios, we can make multi-scenarios of yield and the greenhouse gas efficiency. But in this case, and using this fine resolution three-dimensional model, we are facing high computation requirements. This moving us to move to use machine learning to simplify the computation power. If our data set is already existing but has some missing data, so we are using machine learning like LSTM to fill the missing data and repeat again the process-based model and the machine learning. Sorry. But the specific challenges here is to collect high quality and real-time agroforestry and monocrop and the microclimate data set, and the complexity of parameterization, and to integrate another advanced monitoring technologies. But in this case, therefore, we can find that data is the bottleneck, and we are willing to collaborate with other agroforestry experts to collaborate in this important point. If we see some results from the data set, we can see that moving away from the tree strips, we can see differences between agroforestry and monocrop, where the yield increased with increasing distance from tree strips, and also using the orientation windward achieved higher yield compared with leeward. And also, if we moving the crop protein, we find the vice versa trend, where agroforestry system achieved the higher yield and the low protein content, but there is a trade-off between both. HiSafe also can get detailed outputs like carbon storage and different tree components, which is important in carbon sequestration, water flux and nitrogen flux, and also intercepted radiations. These detailed outputs facilitate the analysis and the complexity analysis of tree, crop, and the climate interactions in agroforestry systems. It also enables us to calculate the land equivalent ratio by using the light capture in the uptake and water uptake.
You have 1 minute. Ahmed,
Yes,
have 1
yes,
minute.
Monique. Okay.
1 minute.
Okay, machine learning models. We trained the different machine learning models and found that Stockton Stimble is the best model achieved robust accuracy. So hybridization help us to fill the missing data and reduce the computation power, simplify HiSafe model optimization and outputs, and they can bridge the limitation of process-based model. We found that the feature the most important predictors that stands soil depths, orientation, solar radiation. At the end, we parameterized the HiSafe in Germany, in Windhausen, in Germany, and build the hybrid approach with machine learning. But next step, we are continue to refine this approach, and we are willing to scale up our approach in different environments. And the last step, we will integrate in a user-friendly web interface to enable other non-experts to use our approach. So we are willing to collaborate with other experts over the globe. We have our related publication in hybridizing machine learning with crop models, like multi-model ensemble with machine learning, integrating AppSim and other, integrating machine learning with multi-model ensembles and remote sensing. But this for monocrop, so we are willing, we are working to upgrade for the agroforestry more complex systems. Thank you for attention and sorry for this.
Thank you, Ahmed. We have time for one question. Just one?
Yeah.
We have one question.
Thank you so much for the nice presentation. I'm interested to know how those low ground interaction has been captured in HiSafe, because like is it 3D or is from the routine of the sticks? Because it is adapted on the routine.
Sorry, I couldn't hear you well. Can you please?
Let me make it.
Please,
I wanted to know how does the HiSafe handle below ground interactions of the roots? Is it 3D or 2D or 1D? And how does it differ with the sticks? Because it is adapted from stick modeling.
Yeah, HiSafe is a hybrid model integrating sticks crop model with safe tree model. So when we are using HiSafe, first we need to calibrate the sticks model in monocrop. Then put this parameterized variables from sticks model in HiSafe. Okay. HiSafe, we should start with a simple unit. For example, cell. if we selected one cell like 1 meter in 1 meter square as a cell resolution. We can replicate and increase our system to include this. But the main driver for using this is to use detailed data set of soil, weather, crop rotation, and the other management factors, and also the tree initialization. The tree strip orientation is very important. The tree species, the tree heights, the age of tree. Okay, detailed data set. And the latest version of HiSafe, which is version 4.3, is more robust than the oldest one. It included many types of his tree species and could be used easily over R script to be used and analyzed and visualized easily. Yeah.
Thank you, Ahmed. Thank you for the question. Now we go to the presentation from Mark Blondy.
I'm Mark Lundy. I'm from UC Davis, and I'm an agronomist in the Department of Plant Sciences. I work primarily in cool season cereals in California. So wheat and triticale. I kind of have a wide range of research topics that include late stage variety development, G-body interaction, precision ag applications, and then measuring environmental impacts and services potentially from these cropping systems.
I have to ask Ahmed to kill his.
Sorry. Okay, could you stop sharing your screen so we can put the other slide up?
Ahmed, are you there? We're trying to kill here, but maybe you have to do that. Ahmed, are you there?
Wait to the bottom. I'll keep talking.
Okay, please.
I'm actually talking without slides so we can make sure we keep moving forward. Okay, so within that broad range of things that I'm working on, one of the unifying concepts is nitrogen use efficiency. And I use remote sensing tools and crop models to understand G-body interactions and precision farming. And recently we've been using combinations of crop models and remote sensing to develop remotely sensed nitrogen nutrition index, which I'll explain here in a second. It'll be harder to explain that without slides.
Whiteboard.
Yeah, there's whiteboard. I was raised with chalkboards, so I remember that. So if we have to go there, we will. But what I'm talking about, a lot of what I'm seeing and hearing at this conference and elsewhere right now is more on the model integration, which we have some of, but I'm happy to follow up with. But I'm really presenting on a potential application. Why would we want to do that? What could we use with that information? So really, what's the relationship between nitrogen nutrition index and nitrous oxide emissions? And can we use that measurement to help us inform nitrous oxide emissions probabilities? That's very well timed. Because I want to explain what nitrogen nutrition index is, if you're not familiar with it. Basically, it is clicker. We're gonna skip. Thank you to my collaborators within Acknowledge the University of Hawaii, here at CIMMYT and UC Davis. I'm gonna point this there and doing it right. We're doing better without technology, I think.
Very good.
Okay, there you go. All right, so I already described this and that, and now we really want to dive into what is the nitrogen nutrition index. It's basically just a method for determining whether a crop is deficient or sufficient. It's pretty straightforward, based on the carbon to nitrogen ratio in plants, which should be biochemically fixed within a crop species. And so empirically derived critical nitrogen dilution curve is created basically by multiple harvests of biomass across different rates of nitrogen, hopefully multiple environments and genotypes, and then determining where biomass is no longer increasing and you're getting luxury consumption of nitrogen. So that threshold has bounced around a lot in the literature over the years. So that's been one limitation of using NNI. But through meta-analysis, Ignacio Sampiti and some others in the last couple of years have been showing that that actually is much more stable if you combine a lot of data sets, both for maize and for wheat. And indeed, we popped that into our data set in California and it worked very nicely. Oh, I didn't actually tell you how to calculate it. Whoops. It's an index. So if you are above threshold, you're greater than 1. If you're below, you're less than 1. And before we get to the hypothesis, what are the current ways that we estimate N2O emissions? Pretty coarse. You're probably familiar with the fact that N2O is 2 orders of magnitude less than what's in the plant system, 3 orders of magnitude less than what's in the soil system. So you're really literally measuring a needle in a haystack. And what we are trying to use to do that historically has been just emissions factors based on nitrogen rate over big empirical data sets. We can improve on that with N-balance, so just trying to get a little bit better understanding of inputs and outputs of nitrogen, but still pretty coarse. And then you get lots of coefficients for tillage and different crops and different crop systems and rainfall environments. But basically, the core understanding is pretty coarse. So our hypothesis is if we could use a physiological measurement, which neither of those are, that actually asks the plant physiology whether you are at luxury uptake, you would probably have a better predictor of nitrous oxide probability, emissions probabilities. And then because NNI is more of a physiologically based measurement, whereas N-balance is more of an agronomic measurement, they're likely to be additive and complementary measurements. So those are our hypotheses. To test it, we've got a global data set from 42 studies, 84 site years, relatively limited because we had to have N2O emissions and uptake, different rates of nitrogen and yield. So that narrowed us down. But we used the same critical nitrogen dilution curves that I described above for wheat and for maize that was published a couple of years ago by Ignacio Sampiti's group. So this is what the data looked like in its raw form, with biomass and nitrogen concentration on the horizontal and vertical axis in those critical nitrogen dilution curves. And then if we take the NNI that we calculate from that on the left x-axis and the N balance from those same observations and observe nitrous oxide as a response variable, we fit initially a log linear model that's a comparable model to what the previous studies had done. And found that NNI was as good in terms of accuracy as N-balance on its own, and that the approaches are complementary. If you use them together, you're improving the accuracy within this data set. And I know I'm talking to a crop modeling group and I'm presenting a bunch of statistical models, but I really want to get to how we could apply this. And so thinking more broadly, we have a problem, even with those models that I just showed, of pretty low accuracy when we're trying to predict absolute emissions. So if we could change our mindset from trying to get the absolute number right to try to predict a probability, then we might have a more flexible tool. So if we look at this distribution of the observed and predicted in both of these crops, we're underestimated at the high end, overestimated at the low end of the range. I think we do better to focus our analytical attention on the low emission, high frequency outcomes versus the low frequency, high emissions outcomes, which we don't really want to incentivize anyway. So to do that, we used a probit model and another number from meta-analysis, such 1.06 background emission levels from upland cereals globally. So that's our threshold that we're comparing to. What's the probability of exceedance of N2O above that standard? So you can see the darker green is higher emissions, and the yellow is lower emissions, and the data set is dominated by these high emissions events. Expressing that same information in the NNI context, where the probability now is colored red for high probability and blue for low probability. We see that NNI is helping to discriminate those probabilities pretty nicely. And then taking a more physiological biochemical interpretation of NNI, if that one is supposed to mean something, sufficiency or deficiency, and we use that one to segregate the populations, does it actually mean something? Yeah, so we seem like below one, we're getting measurably different probabilities of emissions, and we can do something with that kind of a tool. Briefly, as I didn't present it in as much detail, but as with the log linear models, if you add the imbalance in there, it helps. So we're getting additive information regardless of the model, the statistical model that we're using from the agronomic and physiological measurements. So what can we do with that? And how can we use this to incentivize nitrogen use efficiency in cropping systems? Here I'm giving an example of developing a price coefficient and creating a bioeconomic model where we encourage high productivity alongside low probability of emissions. And so you'll see on the 0 there, it's not good enough just to have low emissions or low probability of emissions. We want to have high productivity and low emissions. And so this is an example of a way that you could create a function that does both of those things out of that unitless probability. And so then if we take those price coefficients and divide them into payment groups based on, yes, we did pay you because you achieved the outcome, the low emissions outcome that we were looking for, or no, we didn't pay you because we could tell that you were a high emission field. And then we actually tested against the average emissions in the data set. Did that actually save or lose nitrous oxide? And you can see that the big group on the far left is where we got the payments correct. The really extended distribution that goes to the far right, that's where we didn't pay and we shouldn't have paid. And then the ones in between were where we got it wrong. But if we actually look at the groupings, we're improving the accuracy, the overall accuracy of the groupings. But more importantly, we are getting the actual emissions more accurately characterized by incorporating the bioeconomic information. So in terms of payments for or against high or low efficiency groups, we were close to 70% accuracy. And importantly, the imbalance becomes less important because the NNI was able to find those extreme outcomes, which are really driving the bioeconomic model. So nitrogen use efficiency is really a unifying concept for a lot of agronomy and cropping systems work. And it has a big impact on greenhouse gas emissions. And I think that if we could have a common currency of measurement of NUE, such as this NNI that could be cheaply, easily, and extensively measured, we could do a lot to build markets and policy and farming systems to focus on that same target. And from what I can see here and in our data sets and elsewhere, I think we're close, if not there, to being able to develop global NNI or NUE metric like this. So sorry to run a little long there. That's it. Thanks.
Thank you, Mark. One very brief question, because we're already a little late. Waiting there. Sorry.
So,
Could you use the critical protein in reasonably well yielding environments to achieve the same thing?
I think you might be able. So the question, you probably heard the question online. If you use critical protein to achieve the same thing, yeah, I think it's a similar approach. But this is something that could be scaled with relatively low data requirement. Thanks.
Can you talk to him later?
Thanks, too. Yes, I encourage you to look for Mark later. And let's. I would like to call Frank Herbert.
Yeah.
Present on behalf of Benjamin Leroy.
Sorry?
Yes, this is. Thank you.
So welcome everyone to this presentation. It's a slightly different content than what we have seen before. It's more on data management. In this case, for integration of for streamlining data integration for crop model application. And I may need this.
I saw that.
I will present that presentation on behalf of Benjamin, who works for Centroid at the Technical University of Munich, but there are a number of other colleagues about this in this study. The presentation has, in principle, two parts. I give first some general information about what you see here, NFDI, National Research Data Infrastructure, and the Fair Agro project, when I go into the details of that, of this presentation. A few words about the NFDI. The NFDI, National Research Data Infrastructure in Germany, tries really to overcome the fragmentation that we have in research data management approaches, research data infrastructures, diverse guidelines for management, data management, heterogeneous standards, etc. Not only within disciplinary domains, but also across disciplinary domains, because we are working increasingly integratedly. So I want to make sure that we don't only develop our disciplinary standards, but right from this moment on, try to become a more standardized interdisciplinary. So it includes university, but also outside university organization, basically everything who's in the research domain active and tries to bring these communities together. It also links up to other consortia outside Germany, and there's one reference here to the European Open Science Cloud, quite an important exchange. They are developing a larger network now with other European partners as well. So the NFDI itself has a number of consortia being funded presently that refer to different course domains: natural sciences, engineering, social science, life science, and the Fair Agro consortium is that one here. That's one initiative within the NFDI. You see the co-funding here for this entire machine is quite substantial, 85 million euros a year for a period of 5 years. That's quite a bit of support in order to advance research data management infrastructures. Fair Agro focuses on agrosystems disciplines, related disciplines, crop production, ecosystems, landscapes. Not going into the details here, basically comprises plant sciences, environmental sciences, soil sciences, looks into different levels of organizations, research spanning across levels of organization. There are a number of data categories that come into the picture if you want to try to harmonize data standards, protocols, guidelines. We have in total about, and that the consortium is growing at the moment, 32 participants from universities, applied universities, research institutes, federal institutes, etc. That represent the different disciplines. So it's quite a good representation of the entire research domain. In Germany, we have a funding of about 15 million euros for 5 years. So that is also quite ample in order to move ahead with this endeavor that we have here. In order to become more concrete, we thought quite a bit about it. How do we have lots of data experts in that consortium? But in order to get that link really established to the research domain, or the agro-system research domain, we initiated a number of use cases with respect to integrated modeling, agronomy, long-term field experiment, pest and diseases, sensor system breeding. And we are expanding this as well by having regular calls to open up to other fields, extreme events, for instance, socioeconomic information, horticultural data, and breeding-related data. And that is not closed. We're still having an ongoing call and try to evaluate the incoming projects. We have, from these use cases, when it comes to crop modeling, quite a number of cases that have a common issue in order to use the data that is available and being provided from the agronomy activities in our crop modeling activities. And that's the second part of my presentation now, because we realize that there are, and we all know that, different data types related to crop trials, related to
data that we get from weather services, remote sensing data, published secondary data, basically, and also published data in scientific articles. We had a presentation just now. And there was a demand actually to get the, now I have another slide here. There are a number of challenges related to the use of those data for our crop modeling activities. And those challenges relate to the findability and the accessibility of those data. There's a low incentive for scientists to publish their data. There's a lack of enforced publication policies, and it's difficult to reach out to producers with respect to legacy issues for specific data. There's also an issue or challenges related to the interoperability. The primary data are low adopted often to annotation standards and therefore difficult to reuse for other purposes. Secondary data, there's also low level of harmonization with respect to established standards, and there's a lack of process integration to exploit sensor data for crop modeling. And there are other issues as well. That's just a selection of some of these challenges. So the demand sort of appeared to develop a pipeline that is standardized, structured, and automated in some way in order to make use of those data for our modeling activities. And also to be able to reuse those standards across different groups that have an interest. So coming back to the crop charts, this pipeline sort of has made the first step in order to use IoT sensor data and sort of bring them into a format, an established format by the Open Geospatial Consortium that already matches some standards and could then be used for the crop modeling community. Related to that is that we have developed a sensor management platform in order to support also those activities. But they are also, that refers to sensor data, they're also manually collected data, they're management data, and those are not so easily sort of transferred through a web service here. In this case, there's more manually work required. And here we sort of support these activities, considering the ICASA standard that most of us know, sort of lower the thresholds in order to put the data, manually recorded data and management data into the ICASA template for using those data then for modeling activities. There's another project going on, and I don't need to go into the details here because Qingqing has presented that in order to extract data from publications with respect to perhaps model parameters that could be interesting, not necessarily extractable from these data, but maybe relevant for certain model application studies. And that's also becoming or is part of the pipeline. And then there is a set of data that we also need for our modeling activities, weather-related data, sensor data, and other data that have already a good sort of standard. They have application programming interface developed, API standards, and so can easily connect it to the core element of that pipeline, which is the ETL library. ETL stands here for extract, transform, and load. And once we have all these elements connected to that library, we can use those standardized data then in order to make the link to the modeling application, in this case, PSAT as a test case, but also for other uses, for instance, for publication of data, from field data, maybe using some additional data, weather data, and then through this pipeline, you may also have an automated way of using your data in publication formats. That we believe supports the data curation effort. It reduces the time needed in order to do that substantially. It will support short-term decision support. And it will also support data publication and maybe other activities related to that. I come back to just a quick reference to the use cases. Different use cases work on different parts of this pipeline and utilize it and develop this further. And there's also a link to external activities, for instance, with respect to the ICASA group, Jeff White, if they continue develop their templates or their standards further. We are in close connection with them. And also with respect to some activities in another consortium with respect to data leakage standards that Contact we have also established. One last comment here, where we are in this process as far as the implementation is concerned. There is a concrete case where this is being now tested with concrete data, IoT data, crop scouting from drones, management data, etc. And then there's a set of outputs generated from this activity when it comes related to concept paper, proof of concept paper, etc., in order to demonstrate the use of it. And then gradually it will disperse into the community, will be used by others. So with this, thank you very much for your attention.
No, please don't go. We have time for a question. Okay, we have a question over there.
In fact, this is super important to have this. That's what caught my attention is this Icasa template for data, which is an ASCII-based format. And my understanding, at least in that, somehow seems contradictory to going to big data and we can make it. Is there plan to go to more digital formats of things?
This goes beyond my depth of insights on these processes. The standards, the Icasa standard, is more relevant for the ontology, for the use of the terms, the abbreviations. I think it's not so much about the format in which it is now presently used. I think the format is not the issue. The issue is that we have a standard for using variables, abbreviation of variables, associated units, etc. And if we have a standard, reach a standard here across groups that produce data, that is great treatment already. And we perform this. I think that, I mean, this is the ETL. We take care of that in order to transfer data in that format so that it's an easy. That's how I understand it, but I'm not the expert. Benjamin can clarify.
Thank you, Frank. I have two questions, very quickly. One is, do you think this is something that other organizations could deploy? This open source, the tools you're using? And
yes.
Can we want to do the same in Wageningen or Siemens or anywhere?
No, that would not be meaningful. Ideally, we could dig up just earlier, the earlier the better. The idea is that it will be open source once it has reached a level of maturity. Then, of course, the idea is open source reusability.
Do you have the condition manager?
Also, model the common standards.
Are you considering different scales, like more breeding trials or other sources of information? Because now that was more kind of fields.
Yes.
Level.
I showed at the beginning that we have different use cases, so we really try to grasp the range of subdomains. We had to start somewhere, but gradually in advance, we have lots of activities in the breeding community already. They come from a different, let's say, different angle. There's also a project within the NFDI that works mainly on breeding and genetic data. So we are in close collaboration with them and also try to utilize that interaction. Advanced settings. Thank you.
Thank you. Any more questions? Right. I want to change the order. Do you mind changing the order?
No, that's fine. If there's another one, someone else.
Yes, there is. Oh, no, we can't change the order.
We can't change.
Let's just wait for a second because the presentation was not on the computer.
A quick comment on Frank's presentation. In Australia, the funding body, like we have an industry funding body that funds a lot of the work, and they're actually mandating uploading of, like they have a data management thing, and they're actually mandating the uploading of data as part of every project. And then also going back and funding institutions to upload past data as well. So with a different approach.
Yeah, we have the approach on that funders really request uploading as providing of data. And you do develop management plans with few proposals. And they are not at the level that they check that after the end of the project, but that may be best.
Well, they're milestones in our project, so we don't get paid if we don't upload.
Okay, sorry to interrupt. But we're now ready to start. Lord is going to present. You have 10 minutes and we did not have questions.
Thank you, Monique. Thank you for having me here. This is about the AgMIP10 version 2, which is an improved data set on daily global weather since 1979. Actually, I was missing Copernicus in your slides, Frank. So maybe it's a little bit.
I'm sure there are other things as well. But that was just a selection of use cases. There are other ones.
Well, a little bit like Copernicus. What is Copernicus? It's actually the Earth observation component of the European Union Space Program, and actually a whole couple of services inside Copernicus, like emergency security, land, atmosphere, marine, and climate change. Well, this is actually done within the C3S Copernicus Climate Change Service was carried out. What that looks like is basically C3S looks at climate information, past, present, and future, and make that available to the user community. So through open data, traceability, and they're also particularly looking at sectoral impact. So they're really making an effort to move from data to information for specific sectors, including agriculture, but also emergency, let's say navigation, all these kind of things. Now, what is AgMIP10 then? AgMIP10 is basically AgMIP10 tailored for agriculture. Now, I don't know lots of people about AgMIP10, but AgMIP10 is the 5th reanalysis of the ECMWF. And a reanalysis is basically a replay of the global state of the atmosphere with a numerical weather forecasting model. But the problem with numerical weather forecasting models is often that they change every 6 months because they have a better version with better physics and higher resolution. So you can build on those things if you want to have something which is consistent through time. Now, those reanalysis, what they do is they basically take a version of those weather forecasting models and they replay the entire atmospheric state through since 1979, basically almost up till today. And this is continuing in real time. So every day there's an update. About 1 week ago, basically, there's an 8 days delay in real time. And that starts in 1979 up till present. Now, why 1979? 1979 was about the point that we had global coverage with meteorological satellites. So that's the reason why they start in 1979, because that's the point where you can really start assimilating data. So it's based on AgMIP10 reanalysis. It's a global daily product with regional adjustments for daytime, nighttime. So when you start aggregating to daily values, because AgMIP10 in itself is hourly, and I think the data model itself is even sub-hourly. But hourly is, for many of us, it's basically too much. Most of our models don't run on hourly time steps, they run on daily time steps. So if you start downloading raw AgMIP10 data, which is also massive, you still need to do quite a lot of work in converting it into daily min maximum temperatures, rainfall sums, radiation sums, etc. That's what we did with AgMIP10. Now it's a 0.1 degree spatial resolution, which is about 10 kilometers on the equator. It has, well, like I said, it's an 8-day delay on real time, operational since 2020. And it was actually developed with input from the JRC Mars team, and also CIMIC was involved in defining the product 5 years ago. We did the first version. And well, actually we're providing support mainly. So it's not a product which is, well, it's a one time there and there's no support. If there's something goes wrong, nobody knows what to do. We're supporting it. So if something breaks, it's up to us to get it fixed. And it happens. Now, what did we do to get from this version 1 to version 2? We had some interviews with key users like FAO, JRC, also CIMIT. We had 51 responses on the questionnaire that I set out. Actually, some of you may even have filled it out. Then we made that into a so-called gap analysis document, which basically lists what is missing, what people were actually want from a next version of the document. Of course, we have some reports by users on the Copernicus user service where they say we found bugs or missing something, and that was also taken into account in the design of AgMIP10 version 2. Now, of course, if you start asking users what they want, get a huge list of what they want. And not all of that we can actually do because of resource limitations. So we have an AgMIP10 version 2, but we also have a document called the service evolution document. And that is where everything that could not be implemented has gone into as recommendations for AgMIP6. Even though it's also already working on the 6 reanalysis of the global atmosphere. Well, what did we change? Well, actually we had 22 variables, we added 5 more. For example, we have 7 variables of 2 meter temperature, normal ones, precipitation, solar radiation, all these kind of things. And we added a couple of 1 for these 5. Most of them could actually be computed from the other ones. But we are providing this as a service for people to not having to compute these values. The reference evapotranspiration panel motif, according to the FAO 56 method, then there is 2 products on relative humidity, minimum, maximum, but we already had relative humidity, but that was actually the relative humidity on specific times during the day. We found, although, that it had some artifacts in there, and these artifacts were not really a bug, it was a kind of feature, but people were having a problem with it. So we're now also providing the min and the max, which does not have these artifacts. Now there's precipitation duration fraction, which tells something about the time of the day that it rains. So it tells something about intensity. And there's the VPD, the vapor pressure deficit at daily maximum temperature. And I saw from the first presentation that was actually one of the best predictors. So it was good that we added it. Well, what else did we fix? Bugs. This is an interesting one. For example, here in Australia, we have here in Australia about 42 degrees Celsius max. That was minimum temperature. And then suddenly we have there in black -45. And that happened kind of often actually there in Australia. But sometimes also happened there in Afghanistan. And certainly we had 2 pixels over here and there in Africa. And this didn't happen in areas which were agriculturally important. So most people never noticed it. But we found out that this was a very, very nasty case of integer overflow in the processing chain. And it was really, really hard to find. Because integer overflows, they don't generate any errors. So you cannot get any errors from the system. And actually, it also happened quite frequently. So this is the number of cases per year that it happened. So we really had to reprocess the whole AgMIP5 database in order to get rid of this. Another one. In red here, we have all the locations where the minimum temperature is greater than the maximum temperature. Again, not really the regions which are important for agriculture, but still you want to get rid of it also because it influenced the region why it's there, also influenced basically all the other regions. Now, a bit technical why that happens. But during the reprocessing, we're basically able to solve it. This was the number of grid cell day combinations in 2023 where this was happening. So that's still almost 23 million pixels, which sounds like a lot, but it's about 1% of the total number of pixels in the product. And in AgMIP5 version 2, we've been almost able to get rid of it. And the fact is you cannot entirely get rid of it because the bias adjustments that are done independently for the different variables. And if you have a very small diurnal range, you can have that actually there is a switch between min and max in the product. Okay, conclusions. Well, AgMIP5 version 2 is fully operational. I expect it to be on the Copernicus Climate Data Store end of April, I hope. You can find it this URL then. I think it is probably the most temporary globally consistent data set for agriculture that's available today. And you can argue about that, of course. But I think AgMIP5 is pretty good. It has 27 variables. It has daily updates. So today, -7 day, you can download it from the Climate Data Store. However, biases exist, particularly for precipitation. So you have to be careful in certain areas with AgMIP5. And that's a problem with numerical weather prediction model in general. And the CDS, the Copernicus Climate Data Store, is not the most user-friendly API. So basically what you get is a bunch of net CDFs. And if you would download the whole AgR5 archive, all the variables, you get about 400,000 individual net CDFs. Now, I've been complaining about this a lot, but I can't change. The only thing I can change is try to make it a little bit easier. And therefore I developed a package which is called AgR5 Tools. You can find the documentation on this Read the Docs site. And AgR5 Tools can do the heavy lifting for you. So you can configure it to say, okay, which variables do you want? Which is the area of interest? What are the years that are important for me? And then AgR5 Tools can do the downloading for you of all the data and store it in a format which is easier to handle for crop models. And what it can also do is it can start a local web server on your machine, and it provides you an API to access the data. So if you get to this particular API on your local machine, you get a JSON response of that particular data on that particular location. And to make it easier even, if you're using a model from Wageningen, which I of course highly recommend, you can just take the AgR5 weather data provider and feed it directly into the model, and it works. Any questions?
We have time for one question. So who has the briefest one? Okay.
I was great. Well, I have 3 questions. So that's
Okay, then maybe not.
This is amazing. We're heavy users, AgMIP10 and AgR5. I wasn't totally clear on what the difference actually is, besides like daily aggregation and some regional adjustments, I think you said.
Yeah.
And then maybe 2 quick add-ons. Chemistry, can you provide ozone? And have you considered back extending before 1979 with some other data just to make it useful for downstream users to have a whole century full of it?
Yeah. First of all, the time zone adjustments, that's basically, we're just adjusting to the local time. So to be sure that what is day and what is night corresponds to the local time zone. So basically we have zones where we have different aggregation intervals. Ozone, we don't have it. You can get it from the Copernicus Atmospheric Monitoring Service, but it's not integrated in AgR5. And your last question was?
Backward integration.
Yes, but we discussed it during the some users. There was not really a lot of requests from users to do that. And the other problem is that AgR5 is actually much less, the quality is much lower before 1979 because there is nothing to assimilate.
In ECMIP, we do that. We backfill for the beginning of the century, but we can still.
Yeah.
So we don't have time for questions anymore, but I encourage everyone to look for our alert on the lunch. And now we go to the last presentation, which is from Batista on behalf of Mehib Kalender.
I think I'll start while we're pulling up the slides. I'm going to talk about a data product called CYBit. CY here stands for crop yield, and it is is there a pointer? Is there a pointer here?
Yes.
Which is it? Can I?
The white. So this one?
This one.
The green one.
That's the first
Very dim. Anyway.
Yes.
Yeah. Well, I'm going to talk about CY where CY stands for crop yield. It's a benchmark data set created by the AgML team. So I wanted to spend a few seconds talking about what AgML team is. It is a new team founded almost 2 years ago with an AgMIP to facilitate development and intercomparison of machine learning models for agriculture. It is a global community of agricultural experts, climate scientists, and machine learning researchers. Right now, we have two main activities going on within AgML. The first one is related to future climate impacts on yields, and the second one is related to regional yield forecasting. And this is this is the activity which resulted in the CY bench dataset. So the motivation behind creating this CY bench dataset is that nowadays machine learning models are increasingly being used to answer agricultural research questions. However, the models and the data associated with these models are not readily available in many cases to facilitate intercomparison of these models. So in order to facilitate that, we set out to create an openly accessible high quality benchmark dataset, which is really the first step in being able to do so. So we hope that this dataset will help in standardizing the data-driven models in agricultural science and also facilitate reproducible model comparisons. Within CY Bench, the data we have can be broadly classified into 4 groups. The crop data, weather data, vegetation, and soil data. The crop data or grain yield is our target. Here you can see the purple color represents static data, which is not time series, and the green color represents time series data. So we have crop calendar and crop masks, temperature, precipitation, solar radiation, and ET. We have a couple of vegetation products like NDVI, normalized difference vegetation index, and a fraction of photosynthetically active radiation. We have some soil attributes, soil moisture, which is temporal, and other soil features, which are more static. These predictors were selected based on domain expertise such that they are important for crop yield forecasting. These are the different data sources that we relied on in creating CY Bench. So first of all, crop yield was mostly taken from national or regional crop statistics. We used AgERA5 for weather. I'm not exactly sure which version, but
the previous 1.1.
And then now Oler just mentioned that they have ET within AgERA5, but I don't think we had that at that time. So we used Aquastat-FAO, which also uses the Penman-Monteith method to calculate reference ET. WISE for soil data and GLDAS for soil moisture. Crop masks and calendars were obtained from World Cereal Project, and the FPAR and NDVI was satellite-based, but ready products to be used in agriculture. So these, we actually considered different data sources for each of these categories, and the choice of data source was based on public availability, its global coverage, how often it is updated, and how relevant it is for agricultural research purposes. We have data cards available for more information on why a certain data source was selected over the others. Now here I show you how the data was prepared. Can you see this thing? I don't, but anyway, so the blue here, the zoom is blocking a little bit. So here it says labels, they're auxiliary data and predictors. So here in the blue section, you can see a map of county level yield. So that's really an administrative region, and it's county for the US, a certain NOTS 3 level for the Europe, and there are different levels for different other countries. So when we obtained the yield data for these administrative reasons, we performed some quality checks. For instance, here it shows a non-zero filtering, which means for the pixels that had zero yield, or in some instances, if the yield did not match up the production area and production, we filter those out. So at the end, you get yield data for each admin ID and year. The second box here shows auxiliary data, which is our crop mask. Essentially a mask for the areas where crops are grown. And then the geometry of administrative boundaries. On the right side, there are predictors. You can see both static and time series predictors. We applied a crop mask to these both static and time series predictors so that they are constrained to the areas where the crop is grown. Pretty obvious step, right? And then once we obtained masked predictors, we extracted and aggregated those data to administrative boundaries so that our spatial resolutions match up. So at the end, we have both time series and static predictors aggregated to admin level. And all of those together give us CYBet, where we have the yield targets and static predictors and time series predictors all in one place, which is analysis ready. Here, this is the coverage of CYBet. We have two crops, maize and wheat. The upper one is maize and the lower one is wheat. We have 38 countries for maize, 29 countries for wheat. Here you can see the colors changing is actually the years. It goes from 2003 to 2023. And even so you can also see that the yield targets are changing over years, even within the same country. So it really varies, like what country has what has yields for what years for which reasons. The colors here are yields in tons per hectare. So you can pretty much see both spatial and temporal coverage with this GIF. So we have this data set. So I wanted to add a little bit on what are we doing or what are we going to do next with the data. So right now we're working on training and evaluating different machine learning models for in-season forecasting of crop yield. So that's work in progress. The bottom three points are what we are going to do next with CYBet. So we could create a hybrid modeling approach, for example, by creating different features from crop models. In-season forecasting is possible with a certain lead time by adding weather forecast for the remainder of the season. And we also plan to increase coverage by adding more countries and statistics as they become available. So if you have a country for which you have yield data at administrative levels, we have a pipeline in place to onboard that. And Monique said I had only 1 minute, but this is the last conversation. Sorry. So anyway, I just wanted to tell you how to get the data. So we have the data available on Zenodo. It's already been downloaded 746 times so far, as you can see. We also have a SciBench library, which will allow you to post-process this data. You can get analysis-ready CSV files, and then here in scibench.agml.org, you can get detailed instructions on how to get started with the SciBench data and use it. We also provide the SciBench library also facilitates different types of machine learning model development. There are some limitations since we are at a time. Briefly, no pest disease management. The crop calendars are static. We haven't differentiated between irrigated and rain-fed systems, and this aggregation may not be suitable for all purposes. Just keep that in mind. With that, thank you to our supporters, and we have a preprint available for this paper on Earth system data science. And then here's our GitHub page. Sorry for taking a couple of minutes longer.
Thank you, Pratishta. Don't go. You can have one question. It was to have time for questions. That's why it's, one question. Anyone? Okay, I've seen the hand. Okay. So, child.
You show the map. Okay, you show the map, for instance, for the in Brazil. And,
The mic.
I'm sorry, but
It's working.
Yeah, but even though there is statistics, for instance, in the Amazon and in the Brazil, and in the right of Brazil, these show you like almost zero yield, and because actually there is no maize over there. In a large part of Brazil, that's true. At least half of this map does not have maize. So I'm not understand too much of machine learning, but how does this, it's not good for the model. I mean, the model it's independent for each county. They predict independently, or for instance, that mistake in the Amazon that you will provide better results for the region that we really have lazy, for instance.
So the crop mask should take care of that part where the crop is missing. I mean, I personally did not onboard Brazil.
Michael, want to talk?
Yeah, Michael, did you want to answer?
Well, yeah, I can comment a bit. So in Brazil, we have also a very tiny, the administrative unit is very, very small. And indeed, the crop calendar then takes care of the regions where the crop is actually grown. But you're right that indeed yield is not necessarily low, but production is pretty low, and that's indeed a challenge for this particular data set in Brazil. Yeah.
Thank you, people. Thank you, everyone, for attending the session. Thank you for the presenters. We're just a little bit late, but we can go to lunch now. And great session. Thank you. Thank you, Pierre, for saying that. Thank you for saying that. No, I interviewed the position.
Yeah, it's what I thought too.
Yes. I was at Pratt for a period.
I remember we interviewed as well.
Yes.
So you made the right choice.
I don't know. No, I like where I am, and it was just, it's I lived with my boyfriend, and he had just changed the positions, but it was a hard choice to make.
So I wish I had your tool before we started extracting all that
I
data.
work with Java and actually, I'm likely going to do the direction of delivered models for the data for Brazil. I don't know, it was chatting with Giannis.
One of the things.
Chatting with Giannis, they are